In previous lecture, we have solved examples from exercise 2.6. Today, we'll study examples from exercise 2.7 of methods of real analysis by R.R. Goldberg. So in that, actually theoretical part for this exercise is nothing but operations on convergent sequences. That is, if limit of Sn is L, limit of Tn is M, then limit of Sn plus Tn is L plus M, limit of Sn Tn is Ln to M, limit of Sn upon Tn is L upon M provided M not equal to 0, limit of mod Sn is mod L, etc. So with help of these exercises, these results, today we'll discuss examples. Okay. So first example, you have it 1 limit n tends to infinity of, say if I take 2n cube plus 5n upon 4n cube plus some n square, okay, 7n square. Right. In this case, what we'll do, we'll take n cube outside from numerator. So this is same as limit n tends to infinity of n cube in bracket 2 plus 5 upon n cube is nothing but n square. Then this is nothing but n cube in bracket 4 plus 7 upon n. Now we know that limit of 1 upon n, limit of 1 by n is 0. So limit of 1 by n square is limit of 1 by n into 1 by n, that is 0 into 0. And its scalar multiple 5 times 0 is also 0. So this will become, this n cube is get cancelled since n is not exactly infinity. So we'll get this is 2 plus 0 upon 4 plus 0, which is nothing but half. So in this way we are applying operations. Say limit n tends to infinity of n square upon n minus 7 n square minus 10. If I take example like this, which is equal to limit n tends to infinity of, by take n square outside from denominator. If I take n square outside, we'll get here 1 minus 7 by n bracket square minus 10 upon n square. Right. Then this n square get cancelled, and then as 1 by n square goes to 0, so we'll get 1 upon 1 minus 0 square minus 0, which is nothing but 1. Next example, if limit n tends to infinity of Sn is 1, then show that limit n tends to infinity of Sn raised to half is also 1. Sn raised to half is also 1. On contrary, suppose limit of Sn raised to half is L. Okay. If limit n tends to infinity of Sn raised to half is L not equal to 1, then limit n tends to infinity of Sn is same as limit n tends to infinity of Sn raised to half its square, which is equal to limit n tends to infinity of Sn raised to half bracket square. Limit of Sn Tn is equal to limit of Sn into limit of Tn. Okay. So by using this result, we will get this, and this is nothing but L square. This is also not 1, since L not equal to 1. Contradiction. So hypothesis. Hypothesis, limit n tends to infinity of Sn raised to Sn is 1, and therefore our assumption is wrong. Our assumption is wrong. What this implies is, therefore limit of Sn raised to half must be 1. Must be 1. Next example, evaluate limit n tends to infinity of square root n into square root of n plus 1 minus square root n. So this is equal to root n into root of n plus 1 minus root n. This is equal to, rationalize this part. Limit n tends to infinity of root n into root n plus 1 minus root n upon root of n plus 1 plus root n into root of n plus 1 plus root n. Rationalizing numerator. So this is same as a minus b into a plus b is a square minus b square. So this is square of square root get cancelled. We'll get root n into n plus 1 minus n upon root of n plus 1 plus root n. This n get cancelled. Now we'll take root n outside from denominator, root n into square root of 1 plus 1 by n plus 1 plus 1. This root n get cancelled and then we'll get 1 upon root of 1 plus 0 plus 1 is equal to half. Equal to half. If limit n tends to infinity of say Sn minus 1 upon Sn plus 1 is equal to 0, then show that limit of Sn is 1. Is 1. Solution. Take epsilon is equal to epsilon n is equal to Sn minus 1 upon Sn plus 1. And then solve this for Sn. Solve this for Sn. What will get? Epsilon n Sn plus epsilon n, okay, is equal to Sn minus 1. Then take Sn term on this side. We'll get epsilon n Sn minus Sn is equal to minus 1 minus epsilon n. And then from this, take Sn outside into epsilon n minus 1 is equal to minus 1 plus epsilon n. Therefore, Sn is equal to 1 plus epsilon n upon 1 minus epsilon n. Taking epsilon n by minus 1 there and taking minus side outside from denominator, we'll get this. And therefore, limit n tends to infinity of Sn is equal to limit n tends to infinity of 1 plus epsilon n upon 1 minus epsilon n. But what is your epsilon n? Sn minus 1 upon Sn plus 1. So by hypothesis, its limit is 0. So which is nothing but 1 plus 0 upon 1 minus 0. Since limit n tends to infinity of epsilon n is equal to limit n tends to infinity of Sn minus 1 upon Sn plus 1 is 0. This is given. And this is nothing but 1. Okay, so here we are taking limit of 1 plus limit of epsilon n upon limit of 1 minus limit of epsilon n, means we are using operations on convergent sequences. Okay. Evaluate limit n tends to infinity of 1 plus 1 upon n plus 1 raised to n and limit n tends to infinity of 1 plus 1 upon, sorry, here raised to n plus 1 and then 1 upon n plus 1 raised to 1. So first, limit n tends to infinity of 1 plus 1 upon n raised to n plus 1. So by using in law of indices, this is same as 1 upon 1 plus 1 upon n raised to n into 1 plus 1 upon n, which is equal to limit n tends to infinity of, if I take limit to be separate, okay, 1 upon 1 by n raised to n into limit n tends to infinity of 1 plus 1 upon n. Then this is equal to e into 1 plus 0, which is equal to e. Okay. Now next one, limit n tends to infinity of 1 plus 1 upon n plus 1 raised to n, which is equal to limit n tends to infinity of 1 plus 1 upon n plus 1 raised to n plus 1 upon 1 plus 1 upon n plus 1. Again, by using law of indices, we are getting this. So what is this? As n goes to infinity, n plus 1 also approaches to infinity. Okay. So I can write this as limit m tends to infinity of 1 plus 1 upon m raised to 1 by m raised to m upon limit n tends to infinity of 1 plus 1 upon n plus 1, or here also m. Since n tends to infinity implies m is equal to n plus 1 also tends to infinity. So I will get this, and then this is nothing but e upon 1 plus 0, which is e. Using identity, 1 plus 2 by n is equal to 1 plus 1 upon n plus 1 into 1 plus 1 upon n, so that limit n tends to infinity of 1 plus 2 by n raised to n is equal to e square. Okay. So limit n tends to infinity of 1 plus 2 by n bracket raised to n, but this is same as limit n tends to infinity of 1 plus 2 by n is nothing but this 1 plus 1 upon n plus 1 into 1 plus 1 upon n raised to n. And then this by using law of indices, we will get limit n tends to infinity of 1 plus 1 upon n plus 1 raised to n into limit n tends to infinity of 1 plus 1 upon n raised to n. This is equal to limit n tends to infinity of 1 plus 1 upon n plus 1 raised to n plus 1 upon 1 plus 1 upon n plus 1 into this limit is e. And then again, as n goes to infinity, n plus 1 goes to by this one, okay, is equal to E into E square. Is it clear? So in this way, just by using simple adjustment, we can easily prove that its limit is E square. Is it clear? Next example, if mod x is less than 1, then show that limit n tends to infinity of x raised to n is 0. Solution: if x is equal to 0, then x raised to n is 0 for all n, and therefore limit n tends to infinity of x raised to n is 0. Case 2, if mod x less than 1 and x not equal to 0, then mod x raised to n plus 1 is equal to mod x raised to n into mod x into mod x. This must be less than mod x raised to n for every n. For every n. Is it clear? And therefore mod x raised to n, which is nothing but mod of x raised to n, is decreasing sequence. Decreasing sequence. Decreasing sequence and bounded below by 0. Okay. For fixed x belongs to -1 to 1 -0, and therefore mod of x to the power n is equal to 1 to infinity is convergent sequence. Is convergent sequence. So suppose limit of this is equal to L. Suppose limit n tends to infinity of mod x raised to n is equal to L. Then limit n tends to infinity of mod of x raised to n plus 1 is also L. Okay. Since if the given sequence is convergent, its subsequence also converges to same limit. Okay. Subsequence of convergent sequence converges to limit of that sequence, limit of original sequence. Okay. By using that, we'll get this, and therefore limit n tends to infinity of this mod of x raised to n plus 1 is written as mod x raised to n into mod x is equal to L. But this is nothing but L into mod x is equal to L, and therefore L into mod x minus 1 is equal to 0. This implies L must be 0 since mod x is not equal to 1, as x is not equal to 1 minus 1. Okay. X belongs to mod x less than 1, x not equal to 0. So we are getting this. So L must be 0. And therefore limit n tends to infinity of mod x raised to n is 0. Is 0. Now we know the result. If Sn is sequence, okay, we know if Sn is sequence such that limit n tends to infinity of mod Sn is 0, then limit of Sn must be 0, and therefore limit n tends to infinity of x raised to n must be 0. Okay, x belongs to minus 1 to 1 except 0. Okay, so from case 1 and 2, limit n tends to infinity of x raised to n is always 0 whenever mod x less than 1. Mod x less than 1. Is it clear? Next example, this is one more important type. If S1 is equal to root 2, if S1 is equal to root 2, Sn plus 1 is equal to root 2 into root Sn. For every n greater or equal 1. Then show that limit n tends to infinity or Sn is convergent, and limit n tends to infinity of Sn is equal to 2. So instead of root 2 here, you can take root of any natural number n greater than 1, whatever that number may be. Even though if you take a greater than 0 also, result is true. Try to prove that. Solution. So here S1 is equal to root 2. Therefore, and Sn plus 1 is equal to root 2 into root Sn for every n greater or equal 1. So S2, therefore what is your S2 is nothing but root 2 into root of root 2. This is your S1 is equal to, which implies S2 square is equal to 2 times S1 is equal to 2 times root 2. 2 times root 2. And this is greater than S1 square, which implies S1 square, S1 must be less than S2. Assume Sn is less than Sn plus 1. Sn is less than Sn plus 1. And therefore, multiplying by root Sn must be less than root of Sn plus 1. Therefore, root 2 into root Sn is less than root 2 into root of Sn plus 1. What this implies is Sn plus 1 is less than Sn plus 2. So we proved for 1, assuming result for n, and we proved for n plus 1. Okay. Therefore, by mathematical induction or principle of mathematical induction, Sn n is equal to 1 to infinity is non-decreasing sequence, okay, or increasing sequence. Sequence 1. Now, if I show that it is bounded above, then we are through. Okay. Now, your S1 is equal to root 2 is less than 2. Is it clear? What is S2? So S1 square what is S2? S2 is equal to root 2 into root S1. S2 square is nothing but 2 times Sn. S1 is equal to 2 root 2. This is less than 4 and therefore S2 is also less than 2. Suppose Sn is less than 2. Therefore, root of Sn is less than root 2. And therefore, root 2 into root of Sn, this must be less than 2. And therefore, Sn plus 1 is less than 2. Okay. So, we proved S1 is less than 2. We assume Sn less than 2. And therefore, Sn plus 1 is also less than 2. Okay. 1, 2, 3. Okay. Therefore, by mathematical induction, Sn is less than 2 for all n. And therefore, Sn is bounded above sequence. Bounded above sequence such that your S1 is nothing but root 2. Root 2 is less equal S1, okay, is less than 2 for all n. So all Sn lies between root 2 and 2. Sn is increasing, okay, from 1. So from 1 and 2, Sn is convergent. From 1 and 2, Sn is convergent. Suppose limit of Sn is L. Then L must be greater or equal to root 2 greater than 0 since Sn is greater or equal to root 2 for all n. Okay. This is now 3. Now limit Sn plus 1 is equal to L. But what is your Sn plus 1? Sn plus 1 is nothing but root 2 into root of Sn is equal to L. Taking limit as n tends to infinity, we will get this to be root 2 into root L is equal to L. Squaring we will get 2L is equal to L square. And therefore, L square minus 2L is 0. Therefore, L into L minus 2 is equal to 0. This must imply this L minus 2 is 0 since L is greater or equal to root 2. Okay. And which implies this L not equal to 0. Product of two numbers is 0, so one of them must be 0. So L is not 0, therefore L minus 2 is 0. This implies this L is equal to 2. And therefore, limit n tends to infinity of Sn is equal to 2. Sn is equal to 2. So, with this discussion, today we stop our session here. Thanks for listening lecture carefully. Bye bye.